So thanks for the introduction. As Christina said, my name is Jason Flower, and I work at the University of California in Santa Barbara, in spirit at least, but I live here in Brisbane, and I do a lot of spatial work. I do a lot of marine spatial planning, especially. So that's the main use that I have for geospatial data. And when I'm talking about marine spatial planning, I mean, basically a lot of what I do is help to decide where to put marine parks and marine protected areas in the ocean. But now more and more there's call for not just putting in marine parks, but thinking about where we're going to put areas such as wind turbines or energy generation systems of different sorts and aquaculture. So a more holistic approach. So I use Terra a lot. So this is the repo and the website for the session. So I'm basically going to go through all the material here, I hope. This session's really intended as a beginner's session. So if you already have quite a lot of experience in R or in Terra, then I hope it's not too trivial for you, but you might learn a thing or two along the way. And I've also tried to highlight some of the areas where Terra is different from its predecessor. So there was a predecessor R package called raster, and Terra is basically the new version of raster. So if you're still using raster, I strongly advise you to upgrade because Terra is faster, quicker, and just better. And that's in the words of the creator. It's the same person who did both the packages. And I'm going to speak mainly about raster data today, but we will also come across vector data along the way. And one of the great things about Terra, unlike raster that came before it, is it can handle both vector data and raster data. So we're going to cover everything that is here. So what is a raster? Creating and loading rasters, so really starting at the beginning, and then getting more into exploring the raster data that we load, projecting rasters, because we all know spatial projection is a pain. And then probably one of the best features of rasters are their ability to be multi-layer, so you can have lots of them. And so I'll speak about that. And as it says here on bits on the website, if you're following along on the website and you've been using raster, the previous package, the differences are highlighted when they come across them in the text using this box, this black circle box. There's also a few resources I put on the website there. So I find the documentation within R for Terra it's pretty good, but sometimes quite difficult to understand. So I often end up turning to other resources. And hopefully this website can be a resource for you as well. So I'm going to switch across in just a second to my R studio and start coding. But first, hopefully everyone's done the prerequisites. Really, the only thing you need is Terra. At the very end, I might do an interactive map, and for that you'll need Leaflet. But if you don't have it, really doesn't matter. Just to note, I'm using Terra 1.7.78. So Terra is updated really, really frequently, like sometimes almost daily they have updates. So normally the updates won't be big, but one of the changes he's made recently is the default color scheme. So if you're using an older version of Terra, you might be doing things as I go. Your maps might look just different in color. Okay, so spatial data. The two basic types that we need to know about our vector data. And so for this is things like point data, lines, and polygons. And we use these for things like survey locations, rivers, and boundaries. So denoting country boundaries is the example I've given here. This is Luxembourg. This is built into Terra. And we've got, potentially a river or something denoted using lines. And then these could be your survey locations. Raster data is very different. The key thing to remember about raster data is it's rectangular. So I've just given a little example here of an elevation map in raster data, and you'll see it's a rectangle made up of lots of very small rectangles. So that's the key thing about raster data. And this makes it really efficient to hold lots and lots of data because you don't need to know everything about each of these little squares in the raster. You just need to know how big this rectangle is, how big each of the little rectangles that you're going to put inside it are. These are called cells. And then you just need to tell it rows of values that you're going to put inside it. So whereas for a polygon, we'd actually have to give it the corners of each of these little cells. For a raster, we just give it how big the rectangle is. We let it know how big each cell is going to be. And then we just have some data that's going to fill up that rectangle. So it's very efficient, and it's often used for storing large amounts of continuous data. So things like temperature data, elevation data, you'll often find this. So we're going to get started. So if you have the repo on your computer, the repository that was linked to for this session, hopefully you should have all the data there. And all the code is actually in the index.rmd doc. But I'm actually going to start up a fresh R document. So you see in the RStudio now? Great. And I'm just going to start some coding. So intro, and the fun of live coding. Yeah, that's a great idea. If you zoom in a bit more. How's that? Okay. All right, and I'm just going to save this so it's going somewhere. Workshop. Okay, so all I've done is started up an R document, saved an R document, and I'm going to make my own raster to start with. It's not very often you actually do this, but I'm going to do this as an example of how you can and the possibilities you've got with rasters. So to make a raster or to load a raster, first thing I need to do is actually load the package. So we load Terra and run it. Okay, and then I'm going to create a raster called ras. And to do that, I use the rast function, R-A-S-T. If you're coming from the raster package that came before this, it was raster. No longer, you just need rast. And this is for loading and creating a raster. I'm just going to create a really simple raster. So I'm going to just give it some coordinates, the minimum x coordinate, the maximum x coordinate, the minimum y coordinate, and the maximum y coordinate. And that's all we need to define a raster object, except one more thing, which is the resolution, which is how big the cells are. Remember I said before, each raster is made up of lots of cells, so I need to tell it how big each of those cells are going to be. So I'm going to say 2, which means each cell is 2 units along the x-axis and 2 units up on the y-axis. You can also have different size cells. It doesn't have to be the same on the x and y. So if I went like this, that would mean 1 unit along the x-axis and 2 units up the y-axis. But just for this example, let's just use 2 here. I run that code. Rast, xmin, xmax, xy, min, y. Thank you. Fun of Y code. Yeah, that's definitely it. And yeah, we go. Thank you very much. Okay, so we've created a raster object. Let's have a look at it. So the first thing I generally do with anything I load into R is have a look at what I created. So I just type ras and then run that. And then we see here down in the terminal, I've got some information about my raster. So it gives me the class. So this is what kind of object this is. Like if you had a data frame, it would say data frame there. but we're looking at a spat raster. So this is a new class. If you're coming from the raster package, things before were raster layers. So they're not immediately interoperable. You've got to change the type. These are the dimensions we gave it. So we said the resolution, it's going to be 2 by 2, 2 along the X, 2 along the Y. That's how big each of the cells is. And the extent, how far along the X-axis and how far along the Y-axis it goes, and what those axes are. It's also worked out the dimensions for us. So it knows if each cell is 2 by 2, we're going to have 5 rows and 5 columns. So 10 from 0 to 10 divided by 2 is 5. So 5 columns and 5 rows. So that's the dimensions, and the last part is the coordinates reference system. So it says long lat WGS84. Because we haven't given it any information about where it is spatially in the world, it's just given it a default. So this long lat WGS84 is just the standard coordinate system that's used for things like GPS and so on. So it just gives it that as default. I'm not going to do a deep dive on coordinate reference systems, but I will talk about projecting later. But just for now, that's all we need to know. So the first thing you want to do with any bit of spatial data, or that I want to do at least, is plot it, because that's kind of why we want it. So if I do plot RAS and try and run that, I get an empty screen. And the reason is it hasn't got any values in it yet. So we haven't told it actually what to plot. We've given it some dimensions and so on, but no actual values. And if the question was about raster stacks, I can give a very broad mention here at this point that in here, raster says it has n layer, that value is 1. So there's only one raster in it at the moment. But if you have a multi-layer raster, that means you've got many rasters together. This would be more than 1. And we will come to that later on. Okay. Yeah. When making a raster stack in the raster package, is there a difference between when combining them in Terra using C and the rest? They seem to produce different output. Yeah, so this is probably a bit ahead of what we need to be doing right now, but I'll just mention it. So if you want to make a raster stack, you can do this. You can do, you can do C, which means you're combining them, and you do one RAS and then another raster. And then you'll see the object I get is now I've got 2 layers. And all that's done is put 2 of the same raster together in a stack for us. They're no longer called stacks. So if you're coming from raster, so if you're coming from the raster package, you used to have to do this. Raster stack, and then you'd put a list of your rasters in there. And I can't do it with this raster because they're not, like I said, you can't use them in the separate packages. I think that might help answer the question, but those functions C, ras, and stack, ras, would be the same. Yeah, okay, no worries. So for those of you who blanked out for that bit, no worries. That's something we're going to come back to later on. Alrighty, so first thing we need to do for our raster at the moment is get some values in there. So I am going to just find out how many cells I need to fill. So how many values do I need to give my object? So I'm going to call end cell. This finds how many cells are in my raster. So this will just give us a number. So down the bottom here, I've got 25. Okay, so now let's give our raster some values. So you do this, you go values, and then I'm going to give the name of my raster. So the values for this raster are going to be, I'm going to give it from 1 to 25. So if you've never seen that before, that just creates a sequence of numbers from 1 to 25. So 1 to 25, all the numbers from 1 to 25. So if I run that, and I look again at my raster object, I run ras, I can see now that I've got some extra information. So it now says the minimum value and the maximum value. The first value is 1 and the maximum value is 25. Makes sense. We go with values from 1 to 25. And it's given us a couple of extra pieces of information, notably that it now says the source is memory. And this is, when you're starting out, it's probably not a big thing, but this is really useful and a great function of Terra, that if you got really big rasters, it won't just put them all into your memory, which can overwhelm your computer. So often you're dealing with global rasters or large areas, very high resolution, so they're very big, maybe gigabytes, maybe terabytes. So raster can actually do calculations by taking bits of a raster, bringing it into your memory on your computer, doing whatever it needs to do, and then putting it back on your hard disk. So this is really useful. For a small raster like this that we're creating, it'll just load it straight into memory. Well, we're also creating it, so it's not even on disk to start with. And if you ever want to check, is something actually in memory or is it on disk? There is an in-memory function. So if I run in-memory ras, you'll see I get true. So it is in memory. And later on, we'll see an example of one that is not in memory. There is buried somewhere in the options for Terra a way of, I think you can set a memory limit of how much memory it can actually use, like whether it's 80% of your computer memory or whatever. And I think that will then say, okay, if I'm hitting that value, I'm not going to load it into memory. You can force something into memory as well. And off the top of my head, I can't quite remember how to do that. Normally, if you do any arithmetical operation, so if you multiply a raster by even 1, which wouldn't change it, that should force it to load into memory. We can check that later, actually. It's a really good point, because I've had that problem in the past. Sometimes that is an issue. I'm notably, I'm giving the intro to rasters, not the advanced session in rasters. Okay, so we've got our raster, and now it's got some values. We can actually look at it and see what it is. So we do plot, and then the name of our raster, and we can get a basic plot. So down here, we've got our raster, which you remember we gave it the coordinates, the x coordinates from 0 to 10. We said it could be from 0 to 10 and 0 to 10 on the y. And we said each cell would be 2. So each cell is 2 by 2. And then we've given it values from 1 to 25. And when you do this, it just fills up the values as it goes through the square or the rectangle. So it starts up in the top left here and goes along, just working its way down from left to right. So the highest value is in the bottom right. Okay. So that's how to actually make a raster on your own. It's pretty rare you're going to be doing that. Like I said, it's more as an example of what rasters look like, and just to go over some of the basics. So let's get on to explore some real world data. And this is going to be Great Barrier Reef because I'm a marine scientist principally. So we're just going to look at some temperature data for the Great Barrier Reef. And I've tried to focus this on what I think are operations, certainly operations that I use a lot. So the first thing you often tend to do is you've got a global data set of raster information. So maybe you've got global data of sea surface temperature, and you want to get just your little bit that you're interested in, whether that's Australia, the Great Barrier Reef, or Moreton Bay. So the thing we need to do is get rid of everything we don't want. And that is, in raster terms, that's called cropping, and then masking. And so first up, let's load some sea surface temperature data. So I'm going to call this SST, so for sea surface temperature. And I'm going to do rast. So remember, rast, I load something, and I can give it a file path. So if you're working out of a project which is in the same repository as the data that the same repository that you downloaded, the all the data is in the data folder. So if you hit tab, or if you're in our studio, you should get some file paths. So I'm going to go to data, and the file I'm looking for is this one, GBR temp 2023 05 31 TIFF. So this is a GeoTIFF, which is a super common format for raster data, and you'll find a lot of GeoTIFFs around the place. You can load a lot of different types of file used in Terra. So I'm just going to load this one, and then I'll just give you. So if you want a list of all the things you can actually load using Terra, you can do gdal drivers equals true, and this will give you a very long list of all the data formats that it can load, or it tells you if it can read them in raster format, in vector format, and some more information. Yeah, random little functions. Terra's like a little gold mine. It has all these functions hidden away that you never find unless one day you desperately need it. So I like it for that. Yeah. Okay, let me just have a look. If they're all the same resolution and extent, you could load them all in stack then, and then crop or mask by the desired extent, the area. That is totally true, and that is exactly what we will do later on. Just to note that if you want to load things like a whole group of rasters as a stack in Terra, you no longer need that stack command. You just use the same rast that we just used to load. So we will come to that though. People are obviously way ahead of me. Yeah, if people haven't forked the repo, then you can also download. There was a link to a zip file as well. Yeah. Oh, authentication. Yeah. Yeah. Yeah, so I also included a zip file. So if you unzip all that data, and you'll have to unfortunately navigate to wherever that data is on your computer. Yeah, I mean, don't worry too much about this. This is just if you want to know everything, every type of file that Terra can load, you can run this command gdal drivers equals true. And yeah, it's giving me a big list here. It's kind of difficult to see because it's several columns. So but these are all the different names of types of files. So these are Esri arc files, arc grid info, just all kinds of, apparently 166 different types of file. And some of it can read, some of it can write, some of it can do both. Normally, I would say just try. You just do rast, bung your file in, and hope for the best. It will handle most things. The other important one that it will handle is netcdf files, ncdf. So you don't need a separate package normally to do that. You should be able to just do that within Terra. We just got a few people here who are figuring out how to get the data into their R that we're loading using this raster command. So I'm just going to give everyone a second. Yeah, we're just talking about why colors are different in the plot. So mine is the latest version of Terra, so 1.7.78. Yeah, and I think he introduced the change in 1.7.76, I want to say. So unless you got the very, very latest version, it doesn't, yeah, you just do an update. But you don't need to worry for it. The only thing different is the color, nothing else is. So the default used to be terrain colors. It's now, this is called Viridis, this palette. Right, so we got our data in. Hopefully most people have the SST data loaded. So if you called it SST, let's write SST and run that. And we get this output just telling us like a little summary. So just like we did earlier, gives us a summary of the data. So it gives us all the same information we had before. a couple of things I want to note is the resolution is approximately 0.05 by 0.05. And because this is in long lat, or as it's also known, EPSG 4326, so this is what people call unprojected. So when you get GPS coordinates, this is what it's in. This is degrees, minutes, seconds. So this is 0.05 degrees by 0.05 degrees, each of your little cells. The other thing to note is now we've got source is instead of memory, it's saying a file name. So that means it's not in memory. It's actually still on your hard disk in a file called GBR temp 2023, so on. And again, if we wanted to check that, I can do in memory and SST, and that tells me in memory is false. It's not in memory. One more little tidbit of information here, which I've actually never seen before till I downloaded this data set, is it actually tells you what units are there, Celsius. This is very rare. You're lucky if you got any metadata, let alone units and so on. But I think I got this from NOAA, so they're obviously a bit more organized about their data. How would you go to check the resolution unit? That's a really good question, and I bring it up later. Now I've got to see if I can remember it. If I can see Eric giving me a thumbs up. I'm just going to try and remember how to do it. Yeah, it might be something I have to come back to later. Really sorry. But what we are going to do is plot the raster data we just loaded. So again, plot, and I'm just doing everything in the base plotting package that comes built into Terra. But of course, if you're into ggplot, you can use ggplot. And for those in the room who can see, I'm wearing a TMAP t-shirt. I don't know if you can see online, but I'm a TMAP fan. So I would be doing this in TMAP. But just for simplicity, I'm just plotting in the base package. So now we can see something hopefully familiar. We've got Australia, we've got some temperature data from approximately 9 up to 30 degrees. We can see these coordinates are in longitude and latitude, degrees. It's important to note, and I keep stressing this because I think this is one thing that confused me when I started out with rasters, is that, so all the values you see, every cell within this square that we've plotted has to have a value, because rasters are rectangular by nature. So everything within this plot has a value. Even though the white bits look like there's nothing there, they have a value, and that value is Na. Because we're looking at sea surface temperature, only the areas that are the ocean actually have number values, and everything else is given an Na value. And sometimes that can be a bit confusing. So sometimes what I do is I do plot and plot my data again, and I'm just going to say col Na, so the Na color, and then I give it whatever color I want Na to be. So if I want to make it a bit more distinctive, perhaps I say col Na equals black, and the NAs become black, and it's kind of then a bit more clear. Okay, everything that is black is Na. I'm being really clear. Okay, so we've loaded up some basic data, and one of the first things we want to do, we're only interested in, for this exercise, we're going to say we're only interested in the Great Barrier Reef. And the Great Barrier Reef, it runs somewhere along here, along the coast of Queensland. So what you normally do is you're going to have some kind of polygon boundary for your area. So you might be dealing with a country, you might be dealing with, for me, I'm often dealing with the ocean areas, which are exclusive economic zones. So that's like the country's boundary in the ocean. So we're going to load some vector polygon, let's say boundary data for the Great Barrier Reef Marine Park. So again, this data was with the repository and with the data package if you downloaded the zip file. And you can load it. I'm going to load it into an object that I'm going to call GBR boundary. And I load vector data in Terra using the VECT command, vect. So this is create a vector object. And I just want to be clear for people, you might have used SF for doing vector data a lot. That's what I do as well. But Terra handles its vector data a little bit differently. So it's a different format. So if you have something that is in SF format and you want to get it into Terra, you can also just use this same command. So if you do vect and then just enter your SF data there, it will convert it into a Terra format. So that's hopefully useful for people to know if they're trying to switch between the two. For the moment, we're just loading some data, which in my case is in the data folder. And we're looking to load the GBR, so that's Great Barrier Reef, MPA, Marine Protected Area Boundary GeoPackage. So GeoPackage, a lot of you, I'm sure, are used to shape files, really common vector format, but they're rubbish. Stop using them. You all need to be using GeoPackages because it's much more portable. You don't have many different little bits of files. Anyway, I won't get too on my high horse about it, but it's a good format, and I think it's becoming more and more common now. It's an open standard as well. So I'm going to load that data. Hopefully everyone's been able to find it somewhere on the computer. Should be with all the other data. All right. And we want to plot that data and see where it is on our map of sea surface temperature. So plot the GBR boundary. I'm a terrible note taker, so apologies along the way. I'll probably do a few notes and then forget. So I'm going to plot the sea surface temperature data just like we did before, just using plot. And now I want to plot the polygon, the vector data, on top of that same data. And to do this, I use the lines command. So this is all it's going to say is draw some lines using that vector data on top of the data we've already plotted. So it's not going to do a new thing. So GBR underscore boundary. Okay, so it plotted the sea surface temperature data, and now it's plotted the Great Barrier Reef boundary on top of that as a polygon. So this is the area that we're interested in. So we can see we've got way too much data, and this is really common. You're going to be dealing with a small area, and you just need you don't want to get rid of everything else. So what we need to do is crop and mask the data, and I'm going to explain what that means in just a second. Crop and mask our Australia-wide data. And it's really simple to do, happily. So I'm going to do it in two steps. One is called crop, and I'm going to do it and then kind of explain why we need to do two things rather than just one thing. I think that's probably the easiest way. So I'm going to make a new object called SST cropped. Oops. Cropped. And all we have to do is go crop, and we tell it what we're cropping. So our sea surface temperature data, and then we tell it what we want to crop with. And I enter GBR boundary. So just two arguments. The thing you want to crop, sea surface temperature, that's the raster, and then the polygon data you're cropping to. I run that, and now let's have a look at what we created. So I'll plot again, SST cropped. And again, let's just plot the Great Barrier Reef Marine Park boundary on top of that. So I'll do lines, GBR boundary. And you can see what we've got is mostly data only within the Great Barrier Reef Marine Park, but we've also got all this stuff out here, out in the ocean further out. And the reason for that is, this is the smallest rectangle we can draw around this area. So you remember a raster has to be a rectangle. So I can't just delete this part out here. there has to be some values there because it's got to be rectangular. So it's cropped it, it's removed everything into the smallest rectangle that it can make around that polygon. Okay, so the only extra thing we need to do is get rid of these values. But like I say, we can't literally just cut that out. What we can do is give each of those values that we're not interested in NA values. So that's what the next part does. So next we can go SST underscore cropped, and I'll say masked. Okay, so it's now cropped and masked. And again, really simple function, mask. And we're gonna do the object we created before, SST cropped. And we're gonna mask it again with the GBR boundary. Okay, so now you should have something like, if I plot SST crop to masked, something like this. So now we're back to just the area that we're interested in. And I'll just plot the GBR boundary again on top of that so that everybody can see. So the question from the room was, if you've got huge data sets, and the person here was saying that it's taken about 15 minutes to crop and mask each data set, is there a more efficient way of doing that? I mean, I guess it's a two-part answer. One would be, if you're using all the data as a multi-layer object, all the data sets, if you can put them into a multi-layer, a stack, they were called, that I think will be more efficient than doing each individual raster one at a time. So that's one method. And we'll talk a little bit about multi-layer rasters later. The other thing is, and I can show this right now, and I don't know if this is any more efficient. I think it might be. It depends. Yeah, let me show you. So if you're want to just crop and mask, so this is really common. You want to crop the data and mask it, but you've got to do two functions. Now you could just chain them together. A lot of people pipe things, but you can also just do crop SST GBR boundary. So this is just what we did before. We crop it, but I'm going to tell it to mask at the same time. So I put mask equals true, and that will do the crop and mask all in the same function for me. To be honest, I don't think that would be any more efficient, but that's the only, yeah, that's the only speed gain I can see. Possibly, I think, yeah. Oh yeah, sorry. There was a suggestion that you might be able to run the cropping and masking process in parallel to make it more efficient, to speed it up for large data sets. So that means using multiple cores on your computers. Certainly that would, and last time I checked, they were trying to build some of that functionality into Terra. So it's possible it already does it, but it's also possible that you'd have to look through the options and find out if there's something you can change in the options that will make that you can say, like, use 5 cores rather than 1, because I suspect the default will be to use just 1 core on your computer, and then if you want, you'd have to go in and change that. So the question is, can you parallelize, because you'd have to kind of split the raster up into pieces. And certainly the answer to that is yes, because that's actually what raster does. The package does, Terra. So if you've got big rasters, remember I said it can hold stuff on disk. So it will load what it needs into memory, do a chunk of the raster, and then offload it to your hard disk again and keep doing that. So it already does kind of some of that, but yeah, like I say, I'm not sure about parallelization and whether it actually does that and has that built in. It's certainly an option for speeding things up. Someone's run a benchmark while I'm talking. Oh my God, someone's way ahead of me. Okay, well, thank you. I run a benchmark on using a single line of code compared to 2 lines of code. Here are the results. Does not seem that much different. Okay, that's kind of what I would think. Yeah, someone was just saying in the room that if you've got many rasters, you can of course loop things and just leave it running over a loop. That's often a good method. Yeah, I mean, my preferred method is if you've got a whole stack of rasters, is to literally try and stack them together and do the same operation through the whole stack. I think that's probably the most efficient way of doing it. But if you've got like huge, each raster is huge, that might be difficult to even stack them. So, anyway, just make sure when you've done it, you save it. Key point. All right. So obviously there's a lot of advanced users in the room, so apologies if this is trivial, but hopefully still learning a few things along the way. I'm just gonna, we left off with cropping and masking in the same command, and I just want to show you that does give the same thing. So there you go, there's a crop, a mask in the one line, and then I've just piped it into a plot. And if you've never seen that, that's, if you've ever used the other pipe, there's another pipe like this that probably looks familiar to most people. That's from Magita. It's a separate package. So now built into R, you can use this internal pipe, which has most of the same functionality, but not quite all. But it does mean you can pipe without having to load a separate package. Yeah, I heard that recently as well. Yeah, so this pipe is slightly faster than the Magritta. I'm not sure how you pronounce it, but the other pipe. We've done cropping and masking, and I'd like to move on a bit, unless there's any further questions. And I'm going to talk a bit about raster values and just exploring them. So this is, again, starting with fairly basic things. I think you should note that a lot of the functions within raster are the same as in base. So the base package that comes loaded when you start up R, they use a lot of the same functions. So it just kind of masks that. So it knows that if you tell it, you give it a raster rather than like a data frame, it will use the Terra version rather than the base version. Okay. This does mean if you're not very used to base functions, it's like a little bit more tricky. But so one thing people might have been aware of or might be aware of is you can do a histogram of a data frame using the hist function in base R. So we're going to do that on our cropped and masked data. So remember, now we've got data just for the Great Barrier Reef. So let's just have a look at the distribution of the values that we've got. So we'll run hist on our raster, and it gives a little histogram like this. So what you're seeing here are the temperature values along the x-axis and the frequency of those values along the y-axis. And by frequency, it means how many cells have a value, okay? And in this case, I think they're in 0.5 degrees Celsius increments, these bars. So how many cells are between 20 and 22.5 degrees have a value. And so I would say there's probably about, what, 250, taking my cursor very roughly across. So that gives you some idea of how the values look. And you can, all the same things that you can do with a base histogram, you can do with a Terra histogram. So if I want more detail, I can say breaks equals 100. And so that just gives us a lot more bars. So the 100 breaks in there, and you get a more detailed view of your data. What else can we do? The other thing you might want to see is a kind of more detailed look at how the values, like a tabulated version of the histogram, essentially. So how frequent are your values? So I do FREQ, so a frequency table of my raster values. And so down here, I have the value and how many cells have that value. And these are all rounded. And I think by rounding, they actually just mean lopping off the last digit. So anything from 20 up to 20.999 would be count as 20 in this case. So it's a bit coarse. So if you wanted like higher resolution, more digits, you can just do the same thing. So frequency, FERQ, and then your raster, and then put digits equals, and then the number of digits you want. So let's just do one, just to get one more digit. So this is like digits after the decimal point. So now you can see you've got a much more longer table of your frequencies and the counts there. So that can be useful. I've used that sometimes just to check that the data is looking like I think it should look. And the other useful thing you can do is get the frequency of a particular value. So if I wanted to know how many NA values there are in my raster, I can do value. I can do so I put my raster in there, and then I put value equals NA. And it gives me the count of NA values. And so interestingly, like a lot of the values are actually NA. 50,850 of the values are NA. So if we do N cell, you remember that tells me how many cells are in my whole raster. There's only 63,000 and some change rasters values, and 50,000 of those are NA. And you remember that's because we're only looking at that kind of stripped down the diagonal of the raster. So there's a lot of white stuff, NA values. Okay, so that's sort of basic summaries of the numbers in our raster. We can do some really basic summary stats. Very simply, we run summary. And again, this is same function if you can use, if you've got a, if you're coming from base and you've been doing data frame summaries, you can use the same thing on a data frame, but we're going to use it on our raster. So we enter our raster data there and run that. And it just gives you a basic rundown, the mean, median, mean, and also gives us the number of NAs. So that can be, again, quite useful for, if you've loaded in a raster and just want to get some basic information about it. The other thing you might want is a specific statistical value, often the mean value I'm looking at to get in from a raster. And if you're coming from the raster package, there used to be the very sensibly named, I thought, cell stats function. So you want to get statistics for your cells, cell stats. No longer. Hopefully that is now global. So short for global statistics, which once you know maybe makes sense, but it's not, I don't find it as intuitive. So, but it's easy to use at least. All we need to do is tell it the raster that we want the statistic for. So we need the name of our raster, SST cropped mast, and then we tell it the statistic we want to use. So in this case, let's just get the mean value. And why does it give us NA? So I've run it and it's giving me NA. Now the reason for that is there's a lot of NAs. If there's NAs in something, it doesn't return a value, it just says NA. So we can repeat the function. We'll do global SST crop mast, comma, mean, and this time I'm going to use na.rm, short for NA remove, equals true. So if I run this now, I get my mean value, which you'll see matches what we had up here, 25.19, 25.18745. And again, this is something that's changed from Terra, between the raster package and Terra. The NA remove used to be default to remove was true in raster. No longer. You've got to actually force it to remove NAs. I guess it's trying to make sure people are aware that there are NA values. It's also important to note that what we're getting here, the output from this global call to get this mean statistic, is a data frame. And the reason it's a data frame rather than just a number is because you might be using a multi-layer raster object here. So we'll get to that in a little bit later. But for the moment, what we need to know is it's a data frame, and we can just get the single value if we want. So I want to save this because I'm going to do something with it in a minute. So I'm going to do exactly the same thing I did before. I'm going to do my SST, cropped underscore mast. I'm going to do the mean value. I'm going to do NA remove. Thank you. Remove equals true. And then I'm just going to pipe on the end. So I'm going to do one more thing, as dot numeric. So that changes it from a data frame into just a single value. And I will run that. It'd be useful if I spelled global correctly. Okay, so that should have saved that. Let's just check SST mean. So now you'll see down here, I've just got a single value rather than a data frame. There's nothing else but the value. And that's going to be useful in a second because we're going to do some classification of a raster. Okay, so classifying a raster. So one thing that's, again, I do this quite a bit. I want to say that certain values are going to be, one new value, and certain other values, or a whole range of values, are going to be some other new value. So in this example, let's just say we want all the values between 0 and the mean value of temperature to be cold, and everything above the mean is going to be hot. So that's why we're going to reclassify our whole raster. So the function for this in raster is really easy. It's called reclassify. We're not going to get there quite yet. But if I do, where are you? No, sorry, I'm thinking of the old one. It's now classify. So in Terra, it's classify. If you're coming from raster, the function was reclassify, but no longer. We're going to do classify. The first thing we need to do is build a reclassification matrix, which sounds daunting, or at least it did to me when I first started doing this. But it, geez. There we go. Okay, it's not too difficult. So I'm going to tell it the values, the starting value and the end value, and what I want to reclassify it to. So I said I'm going to do for everything from 0 to the mean value, so which we saved as SST mean. And I'm going to just convert all those values into 1. So everything between 0 and the SST mean is going to be 1 in my new raster. And then everything more than the mean is going to be 2. So I'm going to do everything from SST mean to inf, which is short for infinity. Now I'm just being lazy here. I could go and find what the maximum is in my raster and put that in there, but I can just tell it infinity and it will get everything after the mean and give it a new value of 2. So I'm in my final raster, I'm going to have 2 values. The cold values, everything less than the mean, and the hot values, everything more than the mean. And they're going to be 1 and 2. And I'm going to use my native pipe again. And the last thing I need to do is tell it that this is a matrix and it's got 3 columns. Oops. So matrix, and I'm going to say ncol equals 3. Because if we look at our raster there are 1 column for the starting value, 1 column for the end value, and 1 column for what it's reclassifying it for. So that's how you need to think of it. And that's why I did this on 2 separate lines, because I find it easier. And especially if you're doing lots and lots of reclassification, you want to reclassify it into like 10 different things. It can be a bit confusing. And the last thing, I just do by row equals true. And I'm going to run that. So that's the hard part, building the reclassification matrix. The next part is much easier. I'm going to create a new raster called SST reclassed. And I'm going to do classify my raster data. So we've got SST cropped, masked. So you tell it what you're going to classify, and then you tell it what you're classifying with. So in our case, the reclass matrix, or whatever you named this up here. And that's it. So it's just got two arguments, but one of them is this kind of slightly more complex matrix. Okay. So that should have done it. Let's just have a look. Plot SST under underscore reclassed. And there you go. So you should see the values down the southern half, or the southern part of the GBR, the Great Barrier Reef, are 1, and the values up the north are 2. So that makes sense. The cooler values are down in the south, down towards Brisbane, hotter values up in the north, up towards Cape York and so on. And just as make the plot a little bit like visually easier to understand, we could change the colors. So I just plot it, SST reclassed, and then I do col for color equals, and I just give it the color names in this case. So let's do the cooler colors blue, and the cooler areas blue, and the cooler areas cooler areas blue, and the warm areas red. So there you go. And you can do a lot more fiddling around. I think in the website I have like more details of how to play around with plants to make them a bit nicer, but I'm not really, I don't need to go through all the details of that here if you want to do that. And I appreciate most people are going to go away and use ggplot, whatever it is, to do different plots. I don't think text would work, but that's a good question. So for people online, people are just asking about if when you're doing class matrix, if put in different values in their work. So any value should work, but I'm not sure about words. I don't think it would. No, because it's going to be a matrix. Yeah, you'd have to convert it later. But if you want to like create a nicer plot, it is in the on the website. But where's my cursor? You can actually tell it what your legend should be. So rather than having it say 1 and 2, you can do PLG equals list. So you've got to give it to it as a list and then legend. So it's not very user friendly, this, and probably not the way most people are going to be plotting. But we could say cooler, comma, warmer, and then if I run that, then now rather than the values, it actually says cooler and warmer. But I totally appreciate this format of entering legend items is not super user friendly. There's a lot of material, hopefully more than, or more in depth online if you need. But I'll try and get through just a little bit more. I'd like to get up to multi-layer rasters if we can. If we don't, that's not a big deal. So we are going to go into raster math. So the great thing about rasters is you can do whatever you want with them with mathematics, and it will do it to each of the values in the raster. So if I take our original raster SST underscore let's do the cropped and masked one, and then I do multiply by 2. We get all raster values are multiplied, multiplied by 2. So this can be quite handy. So it just does the same thing to every value in your raster. And so let's say we want to convert into Fahrenheit. So we want to make a new raster that is in Fahrenheit. We'll call it SSTF. And this will be helpful for our poor, confused American friends. So we've got our crop to mass raster, and the conversion from Celsius to Fahrenheit is you multiply Celsius by 1.8 and add 32. So I'm going to put my raster in brackets and multiply it by 1.8 and add 32. And then if I plot that raster, we now see we've got the same data. Nothing else has changed about the data spatially. Just the values are now in Fahrenheit, in units of Fahrenheit. So hopefully, if there's anyone online from North America terribly confused by all this, you're now enlightened. So that's, yeah, really basic raster math. Obviously, you can do more complex operations with your data if you need. The other part I want to talk about that everybody needs to do at some point probably is projecting rasters. Like I said at the beginning, I'm not going to go down the deep dark hole that is coordinates reference systems, because that's a whole session not by itself. But if you're looking at the website, if you go to the projecting rasters section, there's actually an expandable section about coordinate reference systems. I'll just bring it up for 1 second. Oh, yeah, sorry. Can I also use another raster to multiply or any other operation? Yes, you can do all kinds of operations, and yes, you can multiply rasters by other rasters. So if you've got one raster, it would have to be the same extent and the same resolution, but you can multiply 2 rasters together or add 2 rasters together. So if you've got, I'm trying to think where that would be useful. I've certainly done it before, but I can't think off the top of my head. But yes, you can just add rasters, multiply them, but it will have to be the same extent and resolution. Okay. And obviously coordinate reference system.
Someone
That's why did I multiply the raster by 2? That was just as an example. Okay, projecting rasters. That's where it was. I'm just gonna switch screen for a minute. So this is part of the website that got sent around. I think Christina sent it out in the chat at the very beginning. So like I say, I'm not going to go and deep dive on coordinate reference systems, but there's some more information here. It's in an expandable section because, like I say, it's not going to be a focus. I just basically, projections are all about trying to get us from a 3D surface. So unfortunately, the Earth is not flat. If it was, all our jobs would be a lot easier. But unfortunately, we live on a 3-dimensional, not only a 3-dimensional surface, but an uneven 3-dimensional surface. And so projection is all about trying to get that uneven 3-dimensional data and flatten it out. And that's where the term projection actually comes from. If you look here, here's some ideas about the Earth. You can see that it's like a bumpy object. And then this is where the ideas of projection come from, is that you've got a 3-dimensional globe, and then you put a light inside that globe, project it onto a piece of paper, and then flatten out that piece of paper. So this is why we call it project. Let's just have a look at projections a little bit. And to do that, we're going to load a different set of data called some zones data for the barrier reef. And so this is vector data. So again, we're going to use vect. And if you can navigate to wherever you've got your data, so in my case, it's all in the data folder, and we're looking to load the GBR habitat protection zones, this one right here, GeoPackage. So this is just a subset of the data for the barrier reef. I've just downloaded 2 zones. And despite the name habitat protection, you'd think they'd be well protected. The only thing you actually can't do there is trawling. So you can't totally destroy it, but you can do some other stuff. So let's load those zones. And let's just take a look at the object we loaded. Now, we didn't really go into a lot of detail about spat vectors, which is what this is. It's vector data. So it's a spat vector. In this case, there are 2 polygons in it. And we can see here that the coordinate reference system is different to the one we had earlier. Because earlier we had EPSG 4326. We're now in EPSG 3577. And there's a whole bunch of columns with information about this data, but all we need to know is that there are 2 different zones on the Great Barrier Reef. What we're really interested in is the different coordinate reference systems. So let's just try something. Let's plot the SST data we had earlier, cropped and masked. So we're going to plot that. And then let's try and plot the zones we just loaded on top of that. So remember, we do lines if we want to plot some vector data on top. And we don't get anything. And so the simple reason for that is that they're in totally different reference systems. So Terra doesn't know how to plot them one on top of the other. You've got to reproject one of those. You've got to get them both in the same coordinate reference system. A little bit more about the coordinate reference system, though. What is it? What does it look like? Let's find out. So coordinate reference system, CRS. This is how we find out some information about the coordinate reference system of our objects. So if I do CRS zones, it gives me a really ugly output, which is the WKT, or well-known text version of the projection system, which is great if you're a computer, not so great if you're a human being. So you can actually say CRS zones describe equals true. And that will give you something a little bit easier for a person to digest. So now we've got a multi-column object. I think it's a data frame. And it tells us the name of the projection, the EPSG code. And this EPSG code, I think, is short for European Petroleum Standard Group or something like that, because it was the geologists who first developed the systems. And you can see that this is useful for Australia, or it should be used in Australia. So that's just gives you a basic rundown. Now, we've got a problem because, like I said, our SST data is in a different coordinate reference system to our zones data. So if we wanted to look at those 2 things together, we've got to project one of them. So let's just, for argument's sake, we're going to project our SST. So we're going to do SST cropped, masked, projected now. We're going to make a new object. And we are going to do project. And if you're coming from raster package, you might be used to project raster. So no longer have to write out project raster every time, much simpler, you just project. Okay, so project the object you want to project. So our SST cropped and masked data. And then we've got to enter the coordinates reference system of what we're going to project it into. So in our case, we're going to do the coordinates reference system of our zones. So I'm going to run that. And then I'm going to have a quick look at what I created. So SST cropped mask projected is now in that Australian Albers projection that the zones were in. So if I wanted to, I could now plot those 2 things together. And it's really important to note that when you project a raster, you are fundamentally changing everything about the raster, because you're moving it into a totally different coordinate reference system. So here we've gone from degrees into a coordinate reference system that is in meters. So everything is different. These cells, when it says a resolution here, those values are meters. So each cell is 5,430 meters by 5,430 meters, give or take. And if we look at the ultimate, what we've created, the mass projected. So take a look at the original one here. That's the one we didn't before we projected it. And if I run that, you'll see it shifts slightly. And that's just due to the different projection. Everything gets slightly shifted because it's a different projection system, and that's what projections do. The other really important thing to note, and why I keep saying that the rasters are getting totally altered, is if we look at the summary of values. So let's look at the summary of our original raster before we projected it, and then look at the summary after we projected it. So I'm just going to expand the console window here so we can see all the values. So this is the original set, and this is the projected values. You'll see that they're similar, but they're not exactly the same. So each raster value you have in your original has to end up in the new projection. And when it does that, it has to give it a new value because each cell is not going to be perfectly overlapping. So the main thing I want you to take away from this, if you didn't know already, is that when you project a raster, you are changing the values. And that's, so you need to think a little bit carefully about how you do that and really try and avoid projecting rasters as much as possible. Again, there are some more details about methods for projecting because there's different ways that you can project. But again, just because of time, I won't go into the full details here. Yeah, so if you look at the number of cells, they've also increased. So it's kind of proportional. So there's a question in the room, the number of NAs has increased. So in the original, it's 50,000 approximately, and now it's 66. But if we look at the number of cells in our original, that one, and then we look at the number of cells in our new object, hopefully we find it has increased by quite a bit. Yeah. So kind of a proportional increase. So there were 63,000 cells, there's now 78,000 cells. And you might ask, why are there so many more cells? And that's just to do with trying to get everything to line up and still be approximately the same resolution. So this is why it's really important to think about those translations that when you're working with raster data. So one of the most useful things about rasters is that you can have lots of data in a single raster. What we used to call raster stack is now a multi-layer raster object. So let's just load one because the easiest way to learn about that is to have a look. Let's have a look at SST data monthly for 3 years. This is some data I got. And if you're interested in how I created the data and how I got all the data, there's also a file within the repository online that goes through the code I used to download it and make it all. Okay, so we're going to create a new object called SST monthly, and we're going to load, so rast data, and this time we're looking for the monthly temp one. So this one here, gbr underscore monthly underscore temp dot tiff. Just going to give everyone in a room a moment to get loaded. Yeah, there's some chat talk about parallelization. So that's cool. I tend not to work with huge data sets, so I tend not to do much parallelization. Yeah, I found mostly when cropping and masking, I guess I'm just not working with high enough resolution data to have problems with that, or I'm able to, when I'm pulling from global data sets online, I can often do queries that crop it before I get it down. So if people are doing cropping and masking from like using BigQuery, you can actually run SQL queries so that the server does all the hard part for you and you just pull down what you actually need. So I've used SQL kind of queries for global fishing watch data, which is a big set of global, as it suggests, global fishing watch or global fishing data. Where would I find your tips for loading?
I wasn't sure if you if you're talking about something that you made, or the Terra
Oh,
help. You're loading 36 layers together. I think that was
oh
quite
yeah.
interesting too.
Oh, okay. Well, this we'll go into, because now if everyone's managed to load that, if we have a look at that object, we'll see that it just did it. So the data was all together in the stack. So I didn't need to do anything extra special. I just run my rast command and it sorts it out for me, which is, it's really nice. So if you've got, and this is common for big data sets, that they'll be in a stack or in a multi-layer raster object like this. You kind of don't know until you start loading it, but raster will, sorry, the Terra package will sort it out for you. It'll just go, okay, it's a multi-layer raster object. Here we go, I've loaded it. So that's the nice thing. You, like I say, just throw it at the package and hope for the best. It's true, yeah. So someone's in the room was saying it's more useful when raster, the old package, used to tell you it was a stack. So now it's still a spat raster. So it used to be a different class. It was called a raster stack or stack. I can't remember which. So now you've actually got to go, oh, yeah, it's got 36 layers. Yeah, so I agree. It's a bit easier to kind of miss the fact that it is a stack. We have our stack though. Oh. So there's a question in the chat about how you would load a lot of different raster files. So the way I do that, so let's say you've got a directory that has a ton of raster files in it. I think I would do list.files, which is the base command, and then you give it a path and a pattern as well. And that will give you all the files in there. And then I think you'd loop over that. I think you just have to loop over that. Yeah, which is, yeah, it's not what I normally do. And if you loop, you'll normally create a list. So this is, sorry, we're jumping ahead for people who are at a more beginner stage. But if you're looping, you'll normally create a list. So you'd create a list object and load each raster as one element in the list. And once you've got your list object, so if I've got mine, I've just loaded in a whole list of rasters as list of rasters, then you can actually just do list rast underscore and then list underscore rasters. And if I ran that command there, and that was a list of rasters which are all the same extent, the same resolution, and the same coordinates reference system, it would create a raster stack for me, a multi-layer raster object. Okay. So that's something I learned, yeah, when doing exactly this, when loading a whole bunch of rasters. So you'd loop over each raster, load it using rast into a list. So each element in the list is a raster. And then at the very end, you run this command and it will make you one single raster stack. But that's like 10 steps ahead of where we are. I'm just going to see where I end up here. I'll do a tiny little bit more about this, manipulating a raster stack. So sorry, these raster objects, multi-layer raster objects. Yeah, and as someone, Mitch says, you'd be lucky if they're all in the same CRS resolution extent. Yeah, unless someone's already pre-prepped the data for them, for you. But yeah, it's kind of rare you'd end up with just a whole bunch of rasters that are all the same. But then you could loop over all your rasters and crop and mask them all so that they're the same extent, and then make a stack out of them. So that would be another step. I just kind of wanted to show people what this multi-layer object looks like. So we've got our multi-layer object loaded, and what this basically means is that each raster in there is, in our case, it's 1 month of temperature data. But this could be anything. You could have a multi-layer object, which is 1 year of raster temperature data, or 1 minute of temperature data. Yeah, all kind of variables in there. Yeah, I've definitely done that. So the trick is, as someone said, I think Mitch said in the chat, you've got to have all these rasters that you're making into your stack, your multi-layer raster object, have to be the same dimensions, the same resolution, the same coordinates reference system, and the same extent. So let's just plot it to see what that kind of looks like. So if we do plot our monthly data, okay, I'll take a second. Oh yeah, my plot window is a bit small. I'm gonna try and make it a bit bigger. Oh no, doesn't like that, does it? Stop. Oh dear. Shouldn't have done that. Sorry, folks. Oh no, that's okay. Yeah, if you try and resize the window, it doesn't like it. Okay, what you should be getting is let me just, I'll do a quick, I should be able to go from where I was because we were just going to do this library Terra, and then I'll load in the data we have before. My laptop's pretty old. Hello. There we go. Okay, so there's our data. I'm not going to resize the window this time, so they'll be tiny, but the main thing, and you can play around on your own computer. It normally does a 4x4 plot window, so you'll get 4 columns and 4 rows. You can change that and get much more in there, but the idea is it just has a default so that it doesn't overwhelm your plot area and that they're still vaguely visible. So I apologize for people trying to look at this online, but each one of these is a tiny plot of the area we were interested in, and you can plot just a subset of those. So if you only wanted to plot, let's say, we know that there are 32 in there, didn't I say? No, 36. So let's have a look at SST monthly. And we just want the last few. So let's say the last few months. We can use double square brackets. So double square brackets, and then I enter the sequence of rasters I want. So 32 to 36. So that's just the last, whatever, 4, 5. And here we go. I just get those last 5 rasters. That is. So that's useful if you just want to look at a subset of your data. I think the last thing I want to say before I hand over to questions is that you can, of course, do all the same operations that we've been doing on these multi-layer raster objects. So I think we kind of mentioned this at the beginning, but if I wanted to crop and mask all the data, so if I wanted to create a new object called SST monthly cropped _ masked, I do crop and the SST monthly data, what I'm going to crop. So this time it's a multi-layer object, but that doesn't matter. It's just going to do the same operation. Unfortunately, I don't have the GBR boundary loaded, so give me 1 second. Hopefully your computer didn't crash and you still have the GBR boundary loaded. I'm just going to reload it. Okay. And now I'm going to do the crop with the GBR boundary, and let's also mask it just like we did earlier. So mask equals true. Okay, and if again I plot, I'm going to plot a subset of that data that I just cropped and masked. Hold on, not that one, that one. Let's just do the first few rasters from 1 to 4. And there we go in the plot. You see it's now, just like we did before, it's cropped and masked the data just for the Great Barrier Reef boundary. And if you really want to be sure, I could add to this plot the line of the GBR boundary. Now, if you're doing a multi-layer raster plot like this, you can't, well, you can just do this like we did earlier. You can do lines GBR boundary. Oops. tell I'm getting tired. There we go. Oh, I thought it comes up on 1, but it didn't even come up on 1. So what you actually have to do is enter the lines as a separate function within the plot. So I do that, lines, and then the GBR underscore boundary. So I just have to tell it that for each of these plots, it's going to add in this lines function. That's all I'm doing. So it's just the same as we did before, but I'm actually having to give it the lines argument as a function. So now it overwrites it writes on top of the raster, the Great Barrier Reef Marine Park boundary. So got through some of what I wanted. There's a lot more online. I hope the website is a useful resource for folks. There's the next bit goes into zonal statistics, getting some more information. There's some information about making nice maps. Oh, we've got to finish with like a pretty map. So I'll do one last little thing. Plet. So rather than plot, I'm going to do plet. Yeah, no worries. And I've only got my monthly data loaded, so I'm going to do just one of those monthly data. But if you've got the original data, you could just do that. But so it's the same function as plot, but with an E. And if I run that, and you've got the leaflet package installed on your computer, you should get a nice interactive map. And so you can zoom in on your data and find out, well, in our case, what the sea surface temperatures are around the Great Barrier Reef. It's from, the function plet is from the Terra package, but for it to work, you need to have leaflet installed on your computer. Yeah, so if you're running, if you're running the older version of Terra, like before, I think 1.7.76, you won't get a base map when you do that. You can update packages if you want to get the newer version, but I think what you can do is, because so I was doing this and I said, why am I not getting a base map? And I basically put a GitHub issue on Terra, and the person who made it said, yeah, okay, if you want a base map, I'll give you a base map. So now in the newer versions, it actually gives you a base map, but originally it just gave you like a blank. But if you are not getting a base map, I think you can write tiles equals streets there, and that will give you the base, the default base map, which is the OpenStreetMap. And you can do all sorts of other base maps if you look in Plat, and if in the leaflet package, like if you want the Esri world imagery, you just replace that with that, and it will give you the world imagery. You can definitely save. So when you create your data and want to save it, okay. So if you want to create a raster, save some raster data to file, you use write raster, and then you give it the name of the raster you want to write to file. So I'll just do one of those, and then you give it a file name. And you tell it where it wants to go. So I'll put it in data, and I'll just say SST 1 month, and then it knows what to save it as if you give it the right ending, the file. What do you call it?
Extension.
Extension. Thank you. If you have the right file extension there, it'll know how to save it. If you don't, or you can also specify, I think. This is terrible. Auto completes. If I look at right raster, up to override, data type. Yeah, so you can actually specify the file type. And so remember earlier we did this GDAL derivers equals true. So you could specify one of those 169 different file types that you want to save it as. But as I said, you can't always save everything as every
every single file type.
I had no idea there was 169 file types.
And if you want to write a vector, you'll need write vector. And then same thing, you'd enter your data, so GBR boundary and data / GBR new, and let's write, I think I could write a shapefile if you were so deviant. And that would, if I then look in my files list, oops.
Just
Oh,
got
no.
M.
Oh, yeah, thank you. If I look in my files list, it's probably created a messy. Yeah, here we go. My GBR new. See, this is why you don't use geo packages. 5 files for one thing. Anyway, it's created a shapefile there.
Your package, how is it much better? Like I have a friend at work that he only wants to use GeoJSONs. So he's really into that.
Yeah.
And then I don't know, I'm using shapefiles because that's what people are giving me. And I don't know, is the geo package much better? Because then I could just, I don't know, convert things and
Yeah. I mean, I'm just being a bit glib about geo packages being better. But I think they're GeoJSONs are also good. Shapefiles are fine. It's a lot of data comes in shapefile format, where I don't think that's going to go away anytime soon. The one messy thing about shapefiles is you always end up with the multiple file problems, and sometimes people will miss out the projection file, so you then don't know what projection it's in. But yeah, I've had stuff in GeoJSON. It really depends on the database you're querying as well, what format it comes in. It's just I've taken to now saving my vector data as geo packages, just to make it a little bit tidier for my own personal use. So, and it's also a more modern format. So the shapefile format was created, I think, 20, 30 years ago, and there's been some updates, but it's kind of like just getting a bit outdated for modern uses in many ways. I can't remember all the differences, but there is a website online. It's called something like "Don't use shapefile" or "Not shapefile." Yeah, it is literally called something like that. Yeah.
Please. Geo packages are more compressed as well.
Yeah, there's probably better compression. Imagine.
and then instead of 4, you have 1.
Exactly.
Exactly.
That's-
Yeah, that's the big thing.
Yeah, that's already something
Yeah,
I
definitely
would
worth it.
like. And it's converting easy? Oh.
I mean, if
know?
you have something that's in a shapefile, you can just load it in and then save it as a geo package. It would be
Okay.
simple.
All right.
Yeah.
And if you had like 100 shapefiles, you could just write a loop to load them all in and then save them. But yeah, it's probably, I don't know about the file saving. It's probably not huge unless each of the vector files is big. Again, I'd have to do benchmarking.
Awesome. Well, maybe we'll let Jason off the hook for now. Thank you again, Jason. That was so good. Hope to see you at the next workshop. Thanks so much again for joining.
Someone looked like they had a shot glass there. I think it was just coffee though. Yeah. Okay.
Schnapps might be good, but no.
Stretch. Raster layers. People were asking about this at the beginning, so they've probably already tuned out.